Welcome to my second video. This is actually the second in a series I'm calling the Measure the Shape of the Surface of the Earth series. My first video was Flat Earth, a Mountain of Evidence, and in that video I conducted a test in which I attempted to measure across the tops of mountains, and the conclusion I came to was that what I was looking at apparently was showing me that possibly the Earth was flat. I got a lot of criticism from Globe Earth supporters on that video, and a lot of flat earthers who really liked it. Some of the criticism from Globe Earth supporters was extremely hostile and demeaning and using a lot of foul language. But some of that criticism did have was constructive, so it was helpful, and I was able to sift through the ugliness to get to some useful criticism that I used to try to design a new test. Because after stumbling onto the flat Earth, I wanted to find out for myself through empirical evidence collecting that I would do myself, not someone else's, but that I would actually do. That I could collect it and analyze it and come to some sort of conclusion as to the shape of the surface of the Earth based on that empirical data. So, one thing I will say is that, and I don't mean this to be demeaning or dismissive, but flat earthers are making some mistakes with math, and they are. So, and I'll give you an idea of what I mean by that. So one of the pieces of video that I'm going to use in an upcoming video, it's like an observation across the water. It's shot across 31 miles of water over the ocean. And if you go to a circular arc calculator and you calculate the amount, how high the rise is of that section of the arc over 31 miles, it is roughly 170 feet. Now, 31 miles is roughly 165,000 feet. So, over 31 miles, which is 165,000 feet, there's only 170 feet of curvature, which is 1/10 of 1%. It is minute. So it's not detectable by the human eye. And flat earthers use the obscured height as the amount of curvature. And that is actually the mistake that I made in my previous video. I will get into that at a point. So, but for now I'm not going to do that. So, what I do want to say is that I was going to make about an hour-long video again. It was going to have a bunch of my tests and observations and some other observations people had done that had sent me. They had sent them to me. And then I was going to use some stuff that I found on Google, some images and some videos on YouTube, which aren't even mine, but when I started analyzing them, I started seeing something that it seems like nobody else is seeing. Or maybe they are and they're just not sharing it, so I'm not sure. But so I was going to make this video that was going to be an hour long, and the thought of it was just too overwhelming. I never got around to actually starting it. I did a bunch of graphics for it, but making the video I just didn't get around to. So I decided to break it up. And so this video is going to be the first of those broken up segments, and this should be 10 minutes long. I'm always super long-winded, so it could be 15 minutes long, but it's not going to be an hour. And what I'm going to do is show you some, do a Google image search and show you some videos that are taken from the peak of a mountain in Oregon, or some photos actually, still shots. And these shots have been taken by dozens and dozens of individuals who obviously I don't know, and they all look the same, so it's clearly not faked. I think it's a really good source for information. And I'm going to show you what those images look like, and then I've got a scale model of mountains. I'm actually living up in this canyon up here. This is right below Big Bear in Southern California in the San Bernardino Mountains. I'm living up in that canyon, and there's a little school up there. There's a 100-foot long hallway which is completely flat, and I'm going to use that to mimic what I'm seeing in those photographs, which you could see too, but on a flat surface. So I've got little miniature scale mountains. Every 1,000 feet is represented by an inch. So my mountains are 10 inches tall and 11 inches tall and 14 inches tall. And the hallway's about 100 feet long. I think I use about 65 feet of it to do everything to scale, to show you what the view would look like if the Earth were flat, and then you can compare it to these images that you can find of the same shot, and you will see maybe what I see, which is that I'm seeing evidence for a globe, for drop-off, definitely over distance. And this is not the only evidence I found for this. I found more for curvature for the globe, and some of it I think is even more convincing than this. Some of the stuff I collected and some of the other videos that I found on YouTube that I've analyzed, I think are very, very convincing. So I think that's about it. I'm going to go up to that school right now and set up my test, and we'll go over that, and it's fairly easy to understand. And then I will move on to the Google Images and also look at PeakFinder, so that you have a couple reference points for the global, supposedly global view, and the flat view, what I'm going to do with my models. Again, I'm not a glober, I'm not a flat earther, so I'm completely neutral on this subject. I don't really have a belief system as to what the shape of the Earth is. I'm seeing evidence that it's a globe, but I'm not believing in one or the other. I actually had a comment on my video, and someone said this video is one of the best demonstrations of double thought this person had ever seen, which comes from George Orwell's 1984. And double thought is the capacity to hold two competing belief systems in your head. And actually, in relation to that concept, it would be more accurate to say I'm practicing zero thought, because I'm not believing in either the Earth being flat or the Earth being a globe. I'm simply being neutral and looking for empirical evidence. So anyway, I'm going to go back up in the canyon, and as you can see, I actually am in these very tall mountains. They are, I'll spin all the way around here. These mountains are 10,000 feet plus. So, and it seems like a lot of my tests have a mountain theme. So I thought it would be appropriate to be down here in the riverbed shooting the introduction to this video. So now I'm going to go up to the school and set up the models, and we'll go from there. Here we are at the school. This is the hallway. It's about 85 feet long, and it's very level. So I'm going to do two demonstrations for you. One is with these little containers, and the other will be with these little mountains that I made. So as you can see, the little containers, all being the same height on a flat surface, are flat across the top. Now the question is, if I spread these out over a long distance, I'm going to pick up 3 of them, we'll leave the first one. If I spread them out over a long distance, will they remain flat across the top? In other words, will they have the same relationship to one another with regard to height? So I'm spreading these out at about 15 feet between each container, so the total distance is about 45 feet. So what we want to know is, do they remain the same height, or do the distant containers, or especially the most distant container, does it sink down out of that line? And I can tell you right now that it doesn't. So there you can see they're still perfectly level across the top. Move this over a little bit so you can see that. There you go. So they're perfectly level across the top, even though they're spread out over a long distance. And the reason is that objects converge on the horizon directly proportional to how far away they are from the observer. So this first container, we're viewing it at 100% its actual size because we're right next to it. And then the next one might be maybe 90% its size, and then the next one 80, and the next one 70, or something thereabouts, but it's proportional. So each one gets a little bit smaller, but the relationship they have with one another with regard to height, it's going to remain the same. So if they're flat across the top, close together, they're going to be flat across the top far apart. It's just that they're going to kind of look like they're, or that flat line, that line across the top is going to look like it's tilting down towards the horizon, but it will not be curved. It will remain flat. Okay, so the next portion of the demonstration is with these little mountains, and what I've done here is replicate 4 actual mountains that are located in Oregon, and what we're going to do is we're going to make a comparison of real-world photographs that you can find on Google doing a search for South Sister Mountain, which is represented by the first mountain here. So what people do, a lot of people do, groups and individuals, is they hike up to the summit of South Sister Mountain and take photographs. It's a very popular hiking spot. You can find these images, as I said, on just doing a Google image search, and what you're going to see is a lot of images from the summit shooting across to Mount Jefferson, which is represented by the second little mountain here. And behind Mount Jefferson, you'll see Mount Hood, which is represented by the third mountain here. And in the extreme distance, in these images that you can find, and not just a couple, you can find many sources for these images, a lot of different people, groups, individuals. And so the fourth mountain is Mount Rainier in the extreme distance. And what I've done here is I've made these to scale, and my scale is 1 inch equals 1,000 feet. South Sister Mountain is 10,200 feet, so the first mountain is 10.2 inches. Mount Jefferson is, oh wait a minute, that's not right. South Sister Mountain is 10,300 feet, so it's 10.3 inches. Mount Jefferson, the second mountain, is 10.2 inches tall, so that's 10,200 feet. Mount Hood is 11,100 feet tall, so it's 11.1 inches tall here. And Mount Rainier is 14,400 feet, and so my model is 14.4 inches tall. I've also put marks on the hallway, just like I did for the containers, and I've used the same scale to, what we're going to do is we're going to spread these mountains out to replicate to my scale the images that you can find on Google that are taken from the summit of South Sister Mountain. So as you can see right now, it's quite obvious that South Sister Mountain and Mount Jefferson are pretty close to the same height, and Mount Hood is obviously taller, and Mount Rainier is a lot taller, and it's very obvious by looking at these mountains. Okay, what I'm going to do is the same thing I did with the containers. I'm going to collect up 3 of the mountains, and we're going to leave South Sister Mountain because that's where we're going to be viewing from. And again, I'm going to put these in their appropriate locations. So there's a dot on the pavement, and this is Mount Jefferson. And the distance from South Sister Mountain to Mount Jefferson is 39.4 miles, which is 17.4 feet. So that's where my dot is. So, the next mountain is Mount Hood. It's 87.8 miles away. So, according to my scale, that's 38 feet 10 inches. So that's that dot right there. And we'll put that right there. And the last mountain is Mount Rainier, which is 189 miles away from South Sister Mountain. And using my scale, that comes out to 83 feet, or 83.5 feet. And then there's the end of the hallway, so we're just about right. And what we're going to do is we're going to check again and see if the mountains maintain the same relationship with one another with regard to height. Will Mount Rainier still look taller than Mount Hood? And will Mount Hood and Mount Rainier still both look taller than Mount Jefferson? Or will Mount Rainier somehow mysteriously sink down? So here we go. We're at the top of Mount Jefferson, or South Sister Mountain, and we're looking across. I'm going to zoom in now, and you can see that mount. Let's move that over just a tiny bit. There you go. You can see the third mountain back, Mount Hood, still appears taller than Mount Jefferson. And Mount Rainier, way back there at 83 feet, is obviously still taller than Mount Hood and Mount Jefferson. So the relationship with regard to height is the same. Let's get some focus back in here. There we go. Sorry, there's a lot of objects here. I've got the poles and all these mountains, so it's hard to hold focus. But there you have it. Mount Hood is higher at 87 miles away, or in my scale, that would be 38 feet. And Mount Rainier is 83 feet away and still taller. So what we're going to do next is go to Google Images, and I'm going to show you some of those images that I was talking about, where countless people have taken shots, pictures, from the summit of South Sister Mountain of the three distant mountains that I have represented here. And what you're going to see is that in those images, Mount Hood looks about maybe 60 to 70% the size of Mount Jefferson, and Mount Rainier is tiny. Like, it looks like it's a third the size of Mount Jefferson. And my question is, if the Earth is flat, how are people getting those photographs? Because as you can see here, on a flat surface, those mountains, they maintain their relationship with one another with regard to height. Mount Rainier still looks taller. So that's it for this portion. We're going to go have a look at the Google Images, and I'm going to ask you to make up your own mind. You can look at the data and decide for yourself. If you have an alternate explanation as to why Mount Rainier looks tiny, I'm open to any sort of explanation. So I'm not coming to any conclusions here. I'm just sharing my findings. And I have some graphics that I'll share with you as well. And also, we'll take a look at PeakFinder. And then you can look everything over and do the calculations and the fairly simple math and come to your own conclusions. Okay, that's it. On to Google Images. And here we are at Google. I've done a search for South Sister Mountain, as you can see. And here we have the results. And this image right here actually is basically the same image that I used in the demonstration. So it's got Mount Jefferson, Mount Hood. Mount Rainier is really not visible because it's so far away. But what I wanted to do is just show you that there are a lot of sources for these images, and you can look them up yourself. So there we have Mount Jefferson, Mount Hood, Mount Rainier, not quite visible on that one either. There's another one, Mount Jefferson, Mount Hood. There's a little mountain there, but that is actually not Mount Rainier. It's behind that's in the foreground. But there are a lot of images of that similar shot shooting off of South Sister towards Mount Jefferson, Mount Hood, and Mount Rainier. You can find them. I probably looked at maybe 20 or 30 before I found one that was real high resolution that I could use. And I'll show you that in a little bit. Actually, this might be it, but I don't think so. No, that's not it. So let's view this image. Again, there's Mount Jefferson, Mount Hood. Can't quite see Mount Rainier, it's too hazy. But I do have an image that I will show you. But first, actually, let's go to PeakFinder just to verify. So, here we have Mount Rainier, 14,409 feet, 189.9 miles. Just like I had mentioned in the hallway. Mount Hood, 11,161 feet at 87.8 miles. And Mount Jefferson at 10,246 feet, and it's 39.4 miles away. So if we go to information, you can see that the viewpoint information, which is South Sister, is 10,331 feet. So we're actually a little bit taller than Mount Jefferson looking down on it. But you can see here even on PeakFinder that Mount Rainier is tiny and Mount Hood is clearly shorter than Mount Jefferson. So this is already defying what we saw in the hallway, where the mountains that were taller, even when spread out over a long distance on a flat surface, they still remain taller. Mount Rainier was still the tallest mountain. Mount Hood was still taller than Mount Jefferson. But of course this is a computer generated image, so what we need is a photograph, and that's what I have here. Let's see. So this was one of the best photos I could find, and you can barely see Mount Rainier in there. There's that other mountain that's in front of it that I said wasn't it. So Mount Rainier is there, and that's just about the top of it. So isn't that strange? This is what really causes me to think, because in the demonstration I did in the hallway, Mount Rainier was still taller. It was up here somewhere. So why is it so short in this image? And why is Mount Hood shorter than Mount Jefferson? And why is Mount Rainier shorter than both of them? And in fact, tiny, when in fact it's the tallest mountain. This is really, I mean, I've done other tests. I've got other videos that I need to get around to making. I just moved recently and I've been really busy, so I haven't been able to get around to producing the videos. But this is one of many observations that I've looked at that makes me really call into question the whole flat earth theory, because why is Mount Rainier sunken down so low? You saw in the demonstration in the hallway that objects, their relationship to one another remains the same. So Mount Rainier would drop down proportionally to Mount Hood and Mount Jefferson. So they all would drop down, but it would be proportional. So their relationship would be the same. On a flat surface, Mount Rainier would still be the tallest. Mount Hood would be the second tallest, and Mount Jefferson would be the shortest, or equal with where we're filming from. And that's not what we're seeing here. So my question is, why? And the only answer I can come up with is that this very strongly suggests that the Earth is a globe, or that the surface is curved and not flat. But I am open to another explanation, any other explanation, if someone wants to tell me how this observation fits in with the flat earth theory, and can explain to me why Mount Rainier is so small in this image, even though in the test I did in the hallway, the relationships they all remain the same. Mount Rainier was tall, or the tallest mountain, regardless of where I put it. Put it 80 feet away, it was still the tallest mountain. Put it right up next to me, and it's still the tallest mountain. But here, you move Mount Rainier very far away, and it's tiny. So that's my demonstration for now. And I will, consider any sort of solutions to this that include the flat Earth theory. But for now, I'm looking at it and saying that this really looks like we're living on a globe. But I'm open to any sort of alternate explanations. So please leave me comments and let me know what you think. Does this prove that the Earth is a globe or not? Okay, thanks.